So
Okay.
please go ahead.
Okay. Thank you. And hi, first of all, and I'm Gustavo Bertoli. I'm a PhD student here in Brazil in the Aeronautics Institute of Technology. And first of all, it's an honor to be here on this workshop. And I will present our paper, The Improving Detection of Scanning Attacks on Heterogeneous Networks with Federated Learning. This work is part of our current research on machine learning-based intrusion detection systems with my advisors, Lourenço Alves Pereira Jr. and Osamu Saltoni. So this is the agenda for this presentation, starting with the motivation of the problem and the approach chosen for this paper. And then I will present a description of the chosen dataset, and in this case, the rationale why we are using this dataset, a specific dataset. Next, I will present an explanation of the data pre-processing required to obtain our results, and then a detailed explanation about the federated learning setup adopted by us in this work. And finally, the conclusion and the future works based on this ongoing research. So the increasing amount of traffic due to new technologies such as 5G and the large deployment of IoT devices requires fast and automated ways for monitoring security incidents. This increasing was also pointed out in the previous LogStem presentation and the previous David presentation. And machine learning for network intrusion detection is a well-known and active research field that tries to keep up with the pace of these changes, of the network traffic, also providing automated ways for learning the misbehaviors based on the huge amount of traffic data. The use of federated learning as part of our motivation and regarding our specific problem, we think that we inherit the two known advantages of this approach. So we begin with the data privacy. Once the participants of the federation does not need to share their data to a central entity for the learning task. Also, we understand the gains of the efficiency with the reduced amount of data transmitted between the participants and a central server. And another motivation, and specific to the intrusion detection domain, is that we see the federated learning as a feasible approach for intrusion detection because we can learn the diverse behaviors from the participants of the federation. So we understand the federated learning as a technique that enables the distributed intrusion detection system. And it's important to mention that in this domain of intrusion detection, this capability of generalization between multiple agents and multiple environments of deployment is an open challenge. Also, regarding the motivation of our paper and why the scanning attacks, this figure is presenting the cyber kill chain framework, and this framework describes the required steps for a successful attack, and it consists of 7 consecutive phases. So starting with the reconnaissance, then weaponization, next the delivery of a payload, for example, then the exploitation of the target, the installation, then when we think about, for example, ransomware or botnets, the contact with a command and control central, and finally the actions performed. So focusing our work on scanning attacks, we in this framework, the first activity, the reconnaissance, that deals with data collection and in the identification of the target, aiming to identify, for example, the hardware, the operational system, the available services and applications that might be possible to exploit the existing and published vulnerabilities on these targets. So focusing our efforts on these scanning attack detections, we make it difficult for a malicious agent to move on in the attack attempt. So we guarantee the saving of resources and improves the security posture. For the validation of our work, we choose the TON IoT dataset, and it is an appropriate dataset because, first of all, it is a recent dataset being published in 2020, representing the actual heterogeneous network infrastructure composed by multiple layers as the edge, composed by IoT devices, industrial IoT devices, smart home devices, and also the fog and cloud layers. We understand that this kind of network is more similar to the current state of the networks, and also envisions address the understanding of the evolution of the networks. Also, another important point of this data set is the multiple attacks. So it have a lot of attacks in this data set. For example, the denial of service, ransomware attacks, man in the middle. And in our specific case, in our specific interest, the scanning attacks that were performed with two well-known tools, the Nmap port scanning and the Nessus vulnerability scanner. So from the published dataset, we choose a different version that is based on the raw network traffic of the TON IoT, but it extracts the features based on the well-known NetFlow. This different dataset is referenced in our paper and also available in our repository. So according to our objectives, the first step was to maintain just those traffic in the dataset that are of interest. So we kept just the scanning and the benign traffic, reducing the original dataset. Next, the TON IoT description states that there are 5 source IP addresses performing scan attack on this test bed. So based on this information, we confirmed that those 5 IPs are targeting around 346 different IPs, but we considered just those targets with more than 3,000 network traces, reducing to 229 targets. Considering the domain knowledge, we know that the network intrusion detection is an inherently imbalanced problem. But in these cases, the majority of the traffic are benign. And we use this criteria to reduce from the 229 targets to just 13. Then those 13 targets are separated in 13 data silos that represents 13 participants of the federated learning task. And typically all these agents would perform a learning task locally to obtain a satisfactory model to their needs. And from this original setup, we expected to improve individual performances by a federated learning approach. So, for example, Agent 1 would learn a scanning attack on its local data, and Agent 2 also do the same, but both agents may have different background or benign traffic. So with the federated learning, we expected to share the learnings between the participants of the federation. In our case, we have 13 agents that shares the same feature set. That is the reason of the modified dataset that we choose. And due to this characteristic, we define this as a horizontal federated learning setup. So in a traditional learning task, a central participant is responsible to aggregate all data from the participants. However, in this federated learning setup, just the model hyperparameters are shared with an aggregator agent. So on each round of the federated learning task, each participant in this federation retrieves the global model from the aggregator agent and performs the local training, starting from this global model. performing a partial fit on this global model with the local data. Next, these local training models are shared back with the central agent to perform the aggregation with a specific strategy for aggregation that will be available in the next round. So the machine learning algorithm used by us is the logistic regression. So it uses the stochastic gradient descent with log loss. And this decision was based on the algorithm's simplicity and also due to the good performance that we obtained during preliminary tests on the local data. And in our case, the positive class is the scanning attack. So the F1 score is the learning metric in this problem that also addresses the imbalanceness of our problem. And for this federated learning setup, we use the federated average of the participants' parameters, weighted by the imbalanceness of each agent or data silo. That this weighting strategy was the satisfactory one during our test. Now on, in this part of the presentation, all the results were obtained with the following conditions. The federated learning task was evaluated with 50 rounds of interactions between the agents and the aggregator. Then on each round of learning, the local training considers 10 epochs during the stochastic gradient descent. And these epochs uses just 100 samples of each silo as the batch size. The learning rate was defined for training as 0.50. And this evaluation considered all the 13 agents participating in the federation. So this is one of our first results. So we evidenced a small improvement in their F1 score when we compare the federated learning to the traditional local training. It is important to highlight in this case that the federated learning brings also to the table the aspects of data privacy and efficiency. We also report F1 score of 0.93 when considering this as a traditional centralized data approach. And however, we consider this approach as unfeasible for real-world application and for the envisioned distributed network intrusion detection system. And analyzing the F1 score performance agent by agent for the simulated 50 rounds, except for the agent 4, we evidenced that the federated learning approach results in a less variance in performance, meaning better learning and attack detection. And summarizing these results, the majority of the agents participating in the federation presented an improvement of their F1 score, except for 3 agents, the agent 5, agent 8, and agent 9, that kept their performance locally versus federated, and the agents 4, 6, and 13 that reduced their average F1 score. So taking advantage of federated learning on the TON IoT dataset for this binary classification between B9 and scanning traffic resulted in less variability for F1 score in conjunction with the advantage of data privacy. And this makes feasible the understanding that we have of a possible distributed intrusion detection system. And there are still open questions regarding these results and the non-IID characteristics of these datasets, such as the label imbalances and the quantity skew between the data silos, were not stressed to improve the federated learning approach and are open paths for investigation. We understand the federated learning as this feasible approach beyond the advantages of data privacy to enable the learning of diverse participants. So we consider as next steps the evaluation of a multitude of network intrusion detection datasets. So thank you all for your attention, and here follows my email address for further discussion, clarifications, cooperation, or any other needs, and the URL for our repository with the source code for reproducibility. Thank you.
Thank you, Gustavo. Nice and clear talk. Are there questions for Gustavo?
Hello, can you hear me?
Yes.
So yes, I do have a couple of questions. So first, thanks Gustavo for the presentation. I really like the IoT word, let's say. So I was quite curious to see your presentation. And firstly, unfortunately, I'm not too familiar with this dataset, so I would like to ask you some more information of this dataset. Which kind of device are in there? And so this brings then to the second question. Let's start with the first.
Yeah. So this dataset regarding the IoT aspect, they have in the edge layer some smart TVs and some Raspberry Pi devices simulating the transmission of MQTT messages of temperature and so on. And they also implemented some applications that simulates industrial IoT device. These are the devices on the edge layer. On the cloud layer, they have a lot of virtual machines to deal with the edge layer communication and also to manage the interface with the cloud.
Okay, so they are quite heterogeneous. So my question was something that also you already partially answered in the conclusion and future work direction about the generality of this methodology. So I know that you probably don't know exactly how much is general for any possible kind of device or software, but regarding to the different IoT devices, did you see that your methodology is actually able to spot the attacks over all the devices, or there was some differences among them?
Yeah, I understand that we have to evaluate more regarding other data sets. So in conjunction with this data set that we used in this work, we, as next steps, we consider the use of other data sets, and it's part of the chosen modified data set that use those NetFlow features because they published other data sets with the same feature set. And another point that I would like to highlight here is that we kept the scope narrow in this intrusion detection task. So we are focusing just on scanning attacks. So it's common on this domain to see a binary classification between benign and attack in general. So it's a little bit difficult to generalize a learning of this binary classification to other environments. For example, if I have a data set with a specific background traffic and I want to train a model here and deploy in another environment, this capability to generalize, it's very difficult, and it's an open problem in this research domain. So in conjunction with the evaluation of other data sets, we understand that it must be performed this scope narrow for the detection.
Yeah, so I totally agree on that. My question was also focus probably on the last figure you show, the box plot, just to clarify if I got it correct. I don't know if you can open it again.
Let me put here.
Okay, that's one. This one, thanks. So the agents are the different IoT devices.
Yeah, here they are Back to let me move back here just to another slide here.
Just because what I see here is that there are devices that have very high F1 score with little variance, while others have a very high variance.
Yeah, so these agents here are for example, I have to check in the table on the paper, but they are individuals in this test bed. So we have, for example, most of these virtual machines are part of these data silos, and I don't remember each one of the edge devices are also part. So when I mentioned an agent, is the data related with a specific member of this test bed with just the benign and the scanning attack traffic. So back to your question on could you please repeat the question for this?
Yeah, no, so regarding to this figure, so we have 13 agents, and I see that there are very different performance in terms of F1 score. So if you know why also within the same agent, there are so heavy difference, for instance, agent 6 that has this box plot, which is very extensive from 0.2 basically up to over 0.6 as F1 score. And if you investigated a bit on why the different agents have so different performances, like agent 1 is very good in performance as agent 2, while agent 6 much lower performance.
Yeah, it was a question during the review round, and I did this task to understand better this point. And my preliminary understanding is regarding the imbalanceness of each data silo. So we did not explore this more, but some of these agents have really a big imbalanceness with around, for example, 98% of traffic of benign traffic and just 2% of scanning attacks. And we used a weighting strategy for the federated average that takes into account this imbalanceness. So probably a better strategy for this averaging would be required to investigate more.
Yeah, also probably you may try to, let's say, downsample the less present class in order to make it more even and see if performance changes to have a complete overview of the performance, but definitely something interesting. So thank you very much for the presentation.
Thank you for the questions.